This video takes us through a couple of multi-part examples on testing for two means or comparing two means. I shouldn't say just testing. One of them is significance testing related, more significance test related. One is more confidence interval related. Pay attention to the changes in wording and the changes in formula use here. So pause me, give this a quick read. Okay, so we have an experiment here done. We have a treatment group and a control group trying to test out directed reading activities to see if it has an impact on reading scores for students. We have a treatment group that got the directed activities and a control group that didn't. So pause me again, make two lists out of this data. You're going to need two lists. And see if you can run through the phantom steps for this. On your calculator, you're looking for a two-sample t-test. We don't have sigma here, so we can't do a z-test. So make two lists, run the two-sample t-test on your calculator. You'll see the test statistic, the p-value, the averages, the standard deviations all kicked out when you do that. And then see if you can run through the phantom steps for this. Okay, so let's assume that you did that. We're looking to see here, and I'm going to walk through the phantom steps with you. We're looking to see if there's a difference in the mean reading scores. So we want to define the parameter, and notice this is new, and we have to get this right. We're testing a difference in means, mu t minus mu c. I use t for treatment group, C for control group. Where and when possible, don't use mu1 and mu2. Try and give it a little letter name just so you can keep track of the order in which you're doing things. So we're testing mu t, treatment minus mu c, control group, the difference in mean reading scores for third graders who get the directed reading treatment and third graders who don't. I've also pointed out both populations, that's required. So make sure you're fully and completely defining what mu t and mu c stand for. Our hypotheses look like this. The null is that there's no difference, that there's nothing going on, so the difference is 0. In this case, we expect the treatment group to have higher reading scores, so we'd expect a positive difference. You could also write the null hypothesis this way, and the alternative hypothesis this way, if you'd like. That would be acceptable as well. Now the assumptions here, let's try and be a little smart here. We just have a teacher trying this out with two classrooms. There's really not an SRS. So while it might be interesting to that teacher, would have to be careful generalizing it very far. Independent observations, we have two things to check now. One, we want to know that all the students we selected within the treatment and control group are independent of each other. I've made that assumption here, but that might be a stretch in this case. And then the second thing that's new for a two-sample test is that the two groups have to be independent of each other. And again, that might be a stretch here, and the kids talk to each other, but we'd like to know that the kids in the treatment group are independent from the kids in the control group. Normality here, holy cow on my spelling here, the sum of the two sample sizes is at least 30, so it might be reasonable to assume that the distribution of differences is approximately normal. That's an okay way to do it. I've taken a bit of a shortcut here by doing that. Another way would be to make a box plot for both of these. That would actually be a little bit better as I think about it here. And look for rough symmetry and lack of outliers. So a couple of box plots here that actually show that might in fact be a little better than what I wrote here. Name this, it's a two-sample t-test for means. We've been doing one sample up till now, so let's make sure we name it right. Two-sample t-test for means. And then work through the mechanics here, the next part of it. Calculating the test statistic here. Well, it's a t-statistic. And recall from the formulas you saw in the other video that it's x bar 1 minus x bar 2. That's our estimate of the difference. And from your calculator, you should have seen that x bar for the treatment group was 51.48. X bar for the control group was 41.52. So we have 51.48 minus 41.52 divided by the square root of, and again off your calculator you have to get the standard deviations, which are 11.01, squared, students frequently forget to square, divided by sample size for the treatment group of 21, and then we have the control group with a standard deviation of 17.15 squared, divided by 23. Do not do this calculation by hand on your calculator. Use the two-sample t-test to tell you what this is equal to, and this is 2.31. Now again, notice it's actually x bar t minus x bar c minus mu1 mu t minus mu c, but that's 0, so we simply don't show it because in the null hypothesis we're assuming that's 0. So there's a second part to that numerator that we just don't show because it's 0. Now the other thing you're required to do, when you calculate this t-statistic, your calculator will kick out the degrees of freedom, and you need to show that. It's 37.9. That's the sophisticated degrees of freedom calculation. It actually indicates the t-distribution we use to do the math, so that's required. Your calculator then gives you a p-value here, p-value, which is equal to the probability of getting t greater than or equal to 2.31, and that happens to be 0.013. Now that's calculated using the sophisticated degrees of freedom. It is possible to do TCDF on your calculator using 2.31 to something big. If you do that, you need a degrees of freedom. You could pull 37.9 if you use the rule of thumb of the smaller sample size minus 1. You'd put 20 here, and you get 0.016. If you happen to go that route, then you have to show the degrees of freedom that you used here were 20. You get two slightly different answers from a more conservative approach versus the exact correct approach. You just need to be consistent. So if you use your calculator and the calculator degrees of freedom, you show this. If you decide to do it by hand, you show this. Finally, then we have a conclusion at the end here. So the p-value is small enough. We reject the null since the p-value is small, less than a guideline of 5%. We have strong evidence that the directed reading activities improve the mean reading score for third graders in this school. Okay, related to this now, we can come up with a confidence interval, and there's two approaches to this, mentioned in the earlier video. We can use degrees of freedom equal to sample size minus 1 here, or we can let the calculator do the work, in which case we get the more sophisticated calculation. You can do it either way. The key is you have to be consistent in how you present your work. Now, if I use the 20 degrees of freedom, I'll need a t. So we'll do inverse t here, 1.95 over 2 with 20 degrees of freedom. And if you do that, the t star you get is 2.086. So that becomes t star in our calculation. And with that, we can set up a confidence interval. So we're making an interval for the difference in mean reading scores. So the estimated difference is x bar for the treatment group minus x bar for the control group plus or minus t. And then we have that nasty standard error calculation to go in, 11.01 squared over 21 plus 17.15 squared over 23, and if we do all that, we get 0.973 to 18.947. Right, so we're 95% confident that the difference in mean reading score is 0.97 points to 18.95 points. You can also do this on your calculator. It's a two-sample t-interval on your calculator. If you do that, your calculator is going to come up with the degrees of freedom. So the setup looks the same, but you're allowed at that point to leave t star in the formula like this and just show the mechanics. You can get t star with inverse t, but you have to wait to get the degrees of freedom off your calculator. But your work would look like this here if you let your calculator do all the work, which might be preferred in the end. And when you do this, you're still required to quote the degrees of freedom, which which will be 37.9 in this case, the more sophisticated calculation. And because your calculator does the more sophisticated calculation, we get a slightly tighter confidence interval. And again, the key is you have to be consistent. So if you let your calculator do the work, then you quote this confidence interval with these degrees of freedom. If you decide you want to do your own T star, then you're going to quote this confidence interval with this degrees of freedom. And you just have to be consistent in how you write your work. Okay, we have a second example in this video. Actually, I don't think I'll have time to get it done here. So I'm going to pause, and you can pick up the second example in the second video.